Yes, where we had arrived with the harmonic oscillator yesterday was we had established that the expectation value of x squared in the nth excited state was 2n plus 1 L squared. Yes, of course, obviously on dimensional grounds. Yes, that's correct. So, and I said the next item on the agenda would be to connect that back to classical physics. Always a valuable exercise because it tells you something about quantum mechanics. It checks your results. So, of course, classical physics doesn't know anything about 2n plus 1, the quantum number, the excitation number. But it does know about the energy, and we know that n plus a half h bar omega is the energy. So we can write this as 2 times the energy over h bar omega. And this L squared, well, L was defined to be h bar, I think, over 2m omega. I probably had better check that my memory is that is correct, yes. So this L squared is an h bar over 2m omega. So therefore, this is the energy. Various things cancel over omega squared. The 2's cancel. Oops, we need an m. That survives in the algebra. Is that correct? So let's ask ourselves, what do we expect? What do we expect classically? Classically, we have that, what do we expect? We expect that the time average, well, I better write this down now, right? So the time average of x squared, which we'll call x squared bar, since x is a simple harmonic function of time, the time average should be a half, sorry, this thing should be a half of x max squared. Right? The average of cos squared is a half. So if we are writing that x is equal to x cos omega t, it follows that x squared bar is a half of x squared, the maximum perturbation. And what's the energy? The energy classically is a half k x squared, because when it's at maximum extension, it has no kinetic energy. It only has potential energy. That's how much it has. Omega squared is omega is root k over m, so this is a half, so k, omega is the square root of k over m for a harmonic oscillator, that being the spring constant. So if I want to get rid of k, I have to declare it to be omega squared, m squared, omega squared, x squared, right? So that leads to the conclusion that I'm expecting that x squared is equal to 2e over m squared omega squared, which is, but this thing is equal to 2 of x squared bar. So this leads to the conclusion that x squared bar is equal to e over m squared omega squared, in perfect agreement with the quantum mechanical result. Oh dear, we need to put this up, don't we? I've gone adrift by an m squared. Let me get rid of that stupid screen. I can only do one thing at a time. Too stupid. Lights and blinds. Screens. Up. Right screen, left screen, left screen. No, which side? Who are we talking about? You or me? Okay. Right, so there was a complaint. What went wrong? What went wrong was the squares of m. Where did I goof on that? That was because e was a half. No, that was correct. Yes, because it was inside the square rooty sign. Yes, exactly. So this shouldn't have been there. So this shouldn't have been there, and then everybody's happy. Thank you. Okay. So doing this check, right, of what have we done? We have we've checked that a quantum mechanical result agrees with the classical result. Now, actually, amazingly, we've been able to do this independent of n, right? In other words, our classical physics, or a quantum mechanics is recovered classical physics for all n. But we believe that we have to recover from quantum mechanics classical physics only in the limit of large n, because our classical experiments are all ones where we're moving macroscopic bodies around, where the excitation energy will be large in some natural units. So the exercise that QM goes to classical physics for large n, large quantum number. Here's our first example of a quantum number, a relevant quantum number. This is the correspondence principle. Correspondence. And this is an early example, in some senses perhaps not a brilliant example, because we get perfect agreement for all n, right? But all we're requiring is agreement for large n, but we really must have agreement for large n because classical physics is about, it's been validated by experiments conducted at large n. So in the same spirit, so let's talk about now the dynamics of oscillators. So far we have found these stationary states, and I've said several times these stationary states are highly artificial. One way you can see their artificiality is that nt, the state with energy n plus a half h bar omega at time t is equal to that state at time t equals 0 times e to the minus I. Now this is e over h bar t, but since e is n plus a half h bar omega, this is n plus a half omega t. So each and every one of these states has a phase which increments in time at a frequency n plus a half omega t, but the oscillator oscillates at a frequency omega, right? So we have to explain how it is that the oscillator oscillates at a frequency omega, but none of the states evolves in time. None of these stationary states evolves in time with a frequency omega, not one. So and moreover, the oscillators that we're familiar with in the school laboratory, masses on weights and stuff, will have values of n which are like 10 to the 28 or 34 or that kind of simply ginormous values of n. So the frequency here will be stupendous. And nothing in the laboratory is happening at that frequency. So this is total fantasy land. We have to get back to reality. We get back to reality by concentrating on expectation values because it's our connection to classical physics, which is what we are pleased to call reality. So let's calculate the expectation value of x. If we do it for n, we know we're going to get a constant, right? Because when we take the complex conjugate of this complex number, it will multiply together with the complex number over here and make 1. But we already know this. We already know that a stationary state has no time evolution whatsoever. So to get time evolution, what we need to do is say, the state of our system, we have to consider, to have something that moves, we have to consider a system which does not have well-defined energy, which means that its wave function, its state vector, wave function, whatever, is a linear combination of states of well-defined energy. And let's take a simple example. Let's suppose there are just two states present. No, sorry. The proposal is that let's do a sum. Let's do it in all generality. So we're going to write this as an e to the minus I. So this is totally safe. Any state can be written like this. So this is psi, the state of my system at time t. It's a linear combination of states of well-defined energy. There's no question I can do that. It's a general initial condition. And now let us work out the expectation value of x. So what is it? It's going to be the sum an star e to the I n plus a half omega t times n times x times m times am not starred e to the minus I m plus a half omega t. So we can clean this stuff up this is a sum of n and m, of course. It's going to be the sum nm a n star a m e to the, when we put these two together, we're going to have an e to the I n minus m omega t times n x m. And yesterday we already saw what the stylish way is to handle this expectation value here. It's to take advantage of an expression that we showed, that the operator x can be written as L times a plus a dagger, where L is the thing we were discussing earlier on. It's square root of h bar over 2m omega, characteristic length. So, and we also saw what happened when we took an expectation value while we were doing a slightly harder problem yesterday. So this is going to be very straightforward now, because it's going to be L n a m plus n a dagger. All right? And this, remember, a on m produces m plus 1 in an amount, the square root of m plus 1. So this is going to be L root m plus 1 of n m plus the square root. Excuse me, this a produces m minus 1. Whoops, m minus 1. Here I'm not concentrating at all. All right? But it's the square root of the bigger number, the biggest number that occurs. So this is the square root of m. Sorry. A on m produces m minus 1. How much? The square root of the biggest integer that's involved. That's the square root of m. And this is going to produce m plus 1. With the normalization, which is the square root of the biggest number involved, which is m plus 1. So m plus 1. And what we want is we have here a sum of n and m. Let's do the sum over m first, all right? Bearing in mind that that thing is this sum of a delta n m minus 1 and a delta n m plus 1. So we're going to have, for our oscillator, the expectation value of x is going to be, okay, let's take this first one. When we do this first one, sum over n, we're going to have that this is a n star, a how much? In order for this to be not 0, m has to be 1 bigger than n. So this is going to be the square root of n plus 1. And everywhere where I see an m, I'm going to have to write an n plus 1. E to the I. And now, in this case, we've agreed that m is 1 bigger than n, so this is going to be e to the minus I omega t. So that's what we're going to get from this term. And then, sorry, from this term when that goes in there. And now we have to put this in there. And now m is going to be 1, to get a non-zero contribution, m plus 1 is going to have to be n. So m is going to be n minus 1. So we're going to get an an star an minus 1 times the square root of n e, and now in this case m is going to be smaller than n, so it's going to be e to the plus I omega t. And I've lost my L somewhere along the line. Let me reinstate it. Right? There's this L here. I hope we have everything. Slightly scared that we haven't. Let me just check that. No, it seems to be okay. So, and we're still summing, I've lost the sum sign, we are still summing over n. why don't we declare that in this, these are two separate sums, and in this sum, I can introduce a new notation. I can say that n primed is equal to, n is equal to n primed minus 1 in this sum here. And then sum over n primed. And then I can relabel the n primed n, and this term becomes the same as that term, becomes the complex conjugate of that term. So when I do this, I'm going to have a sum now over n primed, L a primed, no, not a primed, a n primed minus 1, a n, that starred, a n primed times the square root of n primed e to the minus I omega t. And the other sum is still over n, and that's a star n a n minus 1 e to the I omega t. But n and n primed are the same they're just dummy indices. We're just summing over them. So this sum is, in fact, the complex conjugate of that sum. These two things are complex conjugates. So what if we write an minus 1 is equal to, say, xn e to the I phi, which we can do where this is real, and this, of course, is real too. So I'm writing a complex number. Sorry, that needs a star on it. Then I'm going to be taking x e to the minus I omega t minus I phi plus this stuff e to the omega t plus I phi, and we're going to be able to combine the two exponentials and discover that x is equal to L times the sum of xn cos omega t plus phi. Sorry, we need a phi n on that. Excuse me. We need a phi n on that. So this obviously needs an n, and that is an n, because each of these complex numbers has its own phase. So what have we discovered? We've discovered that, lo and behold, the position, the expectation value of the position, does oscillate with periodically. This is now we have indeed sinusoidal oscillation. At period 2 pi over omega. In other words, we have in fact recovered classical physics, the classical motion. So the motion at this frequency occurs because of interference, quantum interference between states. So these terms we've got are quantum interference between states of different energy. Right? It was, why do we have states of different energy involved? It was because X, it was because, so when we took the expectation value of X, we got this huge long sum, which involved cross terms between states of, it included the term nxn, right? That was also involved in here, in which the state of a given energy was present on both sides of X. But that made no contribution to the sum, because X is a sum, can be written as a sum of these ladder operators, of these annihilation and creation operators, and if you put the same state on either side, you get nothing. You only get something if the states on either side differ in energy by 1 unit of excitation. So our result all arose from interference between states which differ in energy by one excitation. And it's a peculiar, so that's a very general phenomenon. And a peculiar feature of this problem is that those differences in energy are all the same. They're all h bar omega. And the frequency, well, we'll see this in a moment, the frequency of these oscillations. So all these terms have the same sinusoidal. We have an infinite number of contributions still, but they all have the same sinusoidal behavior. So we've recovered the important feature of a harmonic oscillator, that the period is independent of the amplitude of the excitation. The amplitude of the excitation is controlled by which of these ANs are significantly large, right? Because AN is the amplitude to have energy n plus a half h bar omega. So a highly excited oscillator has the non-zero values of AN are all clustered around a large value of n, and a only gently excited oscillator has the ANs around zero or small values of n being fairly large, and therefore this sum will be dominated by whatever region has the large values of A. But the result we've got is that there's harmonic motion at frequency omega, regardless of which terms in this sum are dominating. And that's this property that the period does not depend on the amplitude. So let's be more realistic and see how much more of classical physics we can get out of this by talking about an anharmonic oscillator. So I introduced harmonic oscillators by saying that they're widespread because if you have a point of equilibrium, if you plot against displacement from point of equilibrium, you plot the force, you have some curve that looks like this and should pass through zero, at the point of equilibrium, by definition of a point of equilibrium. But that if you displace yourself from either side of the point of equilibrium, if it's stable, the force slopes like this. It's positive. Sorry, it really should be negative, shouldn't it, actually, when I come to think of it. Sorry, I should draw the graph this way around, shouldn't I, in order to get a stable force. So if I displace myself positively in x, the force becomes negative and pushes me back. If I displace myself negatively, the force becomes positively and pushes me back. So that's a stable equilibrium. And a harmonic oscillator arises if we approximate the curve of this force versus distance by the straight line that's tangent to it at that point. So basically what we're doing, so any force versus distance curve could be expanded as some kind of a Taylor series, and if we just take the first non-trivial term in that Taylor series, we have a harmonic oscillator. If we take subsequent terms, we will have a not harmonic oscillator, an anharmonic oscillator. And typically, typically the force versus, so for a harmonic oscillator, the force versus distance is a straight line that goes all the way to infinity, which means that in order to pull your spring apart, you have to do infinite work. Because to get x to go to infinity, you have to overcome a force that goes to infinity. So infinite work is required to pull this thing apart, but all real oscillators, all macroscopic ones, certainly you can just break them. So only a finite amount of energy is required to push x off to infinity, and that's reflected in the fact that typically the force versus distance curve slopes over like this. So that if we plot the potential V versus x, in the harmonic case, we have a parabola that looks like this and disappears off to infinity. So this is the harmonic oscillator. But in a real oscillator, the potential curve starts from some finite value at infinity. Sorry, and I need to draw it so it becomes tangent to this, and then disappears off like this. So this is a more realistic curve. And the harmonic oscillator is a good model if the parabola is tangent to the realistic curve over a decent range. That's the main idea. So what we should do is investigate, let's to see what quantum mechanics has to say about more realistic oscillators. Let us take, so this is just an example. Supposing we take v of x is minus some constant a squared plus x squared, and I suppose we need an a squared on top to get the dimensions straight. So supposing we take that to be our potential curve, then we now sit down, we have a perfectly well-defined Hamiltonian, p squared over 2m plus this v of x, but we can no longer solve this analytically any more than we can actually analytically integrate the equations of motion classically in this potential. So in either case, you can't do it. But it's pretty straightforward to solve this problem. HE equals EE numerically. We do it in the position representation. We bra through by x and have that x p squared over 2m E plus x v E is equal to E x E, which turns into, by the rules we've already discussed, this turns into an ordinary differential equation, minus h bar squared over 2m d2u by the x squared plus v of x u is equal to EU, where u, of course, is equal to x E. So this is an ordinary differential equation, second order, etc. And it's linear, and it's pretty straightforward to solve numerically. If you look in the book, there's a footnote that explains how to do that. Now, I should have, I'm afraid, I meant to bring my laptop with the official figures, but when you do this, so by discretizing this differential equation, we turn it into an exercise in linear algebra, which your computer solves. So you write this basically as a matrix, M on U, which becomes a column vector. The value that U takes at the different positions in X is equal to E U. So you turn it into a matrix equation, and computers are very good at matrix equations. When you do that, you discover what the values of E are, and you can also discover what these wave functions look like. And the crucial thing is that you find that if you plot the possible energies, you get a distribution that looks like this. It starts off looking like an equally spaced ladder. For the harmonic oscillator, there are steps here, each one of which is separated by h bar omega. So we start off like that with the spacing given by the harmonic oscillator that's tangent to the bottom of the curve. But as we go up, the spacing gets less and less and less and less and less and less. And what essentially the algebra is doing is giving you an infinite number of allowed energies, or already in a finite range, because this is V naught. Okay, so that potential allows that potential, as x goes to infinity, goes to a finite value. Well, it goes to 0. So this is 0, and I guess this is minus V naught. So the lowest energy is somewhere down here. So with only a finite range in energy, you pack in an infinite number of allowed energies. With a harmonic oscillator, you pack in an infinite number of these things, but in an infinite energy range, because this ladder goes on forever, right up to the heavens. Okay, so that's the first. This is a very generic behavior that we will encounter again in real systems. Now, what's the physical consequence of that? Suppose we have. So now let's say our initial condition is this. that it consists simply of two terms, an of n plus an plus 1 of n plus 1. And so the time evolution is going to be and this one's going in give myself some space, an plus 1 e to the minus I e n plus 1 t on h bar, n plus 1. So that's not a completely general initial condition now, because I'm assuming that there are only two non-vanishing amplitudes. So my state, it happens to be such there are only two possible values of the energy that I can measure. There's an amplitude an to measure the energy en, and there's an amplitude an plus 1 to measure the next highest energy. Okay, so this is kind of a special case. If we now work out what the expectation value of x is for this special case, we find that it is an star e to the I ent h bar n. This is all very similar to the other case, an plus 1 star ei en plus 1 t on h bar x. And then the same stuff on the, and then an e to the minus I ent on h bar. Now, when we multiply this stuff out, we will get, we will quite generally get only two terms. We'll have this on this and this on this. The reason for that is that we will show later on that for that potential, xn, so for the harmonic oscillator, this is true. But it's not only true for a harmonic oscillator that this thing vanishes here. It's going to be true for any potential well which is symmetrical around x equals 0. So this follows from symmetry of v of x, that v of x is an even function of x. So long as v of x, the potential, is an even function, the same behavior at minus x as plus x, this will vanish. We will show this as we go along. I haven't shown it yet, but that will be true. So given that that's so, quite generally, my expectation value here is going to be an star. So it's going to be this on this, e to the I en minus en plus 1 t on h bar times the matrix element nx n plus 1 plus, excuse me, and I'm needing here some an star an plus 1, right? So that's that on that, and then we will have this on this, an plus 1 star e to the minus I en minus en plus 1 t on h bar times n plus 1 and x n. Hope I've done that right. So what do we have now? We have again that this term is the complex, well, we have this term is the complex conjugate of this term. So we're looking at a sinusoidal function plus its complex conjugate. Therefore, we're looking at something which is xn, could be written as xn cos en cos en minus en plus 1 t on h bar plus a possible phase factor, right? Where, and just to be concrete, xn is the modulus of an plus 1. So a plus 1 is a complex number. I have its modulus sticking out here, and I stuff its phase into there. So what do we observe? Again, we have harmonic motion, sinusoidal motion. But look now at the period of this sinusoidal motion. The period of the frequency of this sinusoidal motion now depends on n, because it's the difference of two energies, of adjacent energies, which counts. And as we increase n, according to my bad sketch up there, the difference between adjacent energies gets smaller. So the frequency becomes smaller with increasing n. So we're recovering a classical fact, which is that if you have an anharmonic oscillator of a typical type, and you make bigger, you kick it to a bigger oscillations, its period will slow down. And that's true of an ordinary pendulum. An ordinary pendulum has its highest frequency if you have it go to and fro with a small amplitude that clockmakers make their pendulums go to. But the period goes to, as you increase the amplitude of the oscillation, so this is as it were high omega for a pendulum. As you boost the period to the point at which it's about to go over top dead center, if you make it swing so it goes like this and then like this, the period goes to infinity formally. Well, it does go to infinity. It's hard to do experimentally as you increase the amplitude to the point at which it would go, just keep on going. It had enough energy to go right through top dead center. So this slowing of the period with increasing amplitude is manifested in a standard pendulum, and we see how it emerges from the structure. So here we're learning something important, that the way in which the dynamics is encoded in the spacing of the energy levels of the energies of the stationary states. These are just simple examples of what's totally generic. Okay, something else that we can learn about this anharmonic oscillator is that, so more generally, this was a simple example. I said, let's consider, in order to get something to move, I considered a state that was that had undefined energy. To keep it simple, I took just two non-vanishing amplitudes. There are only two non-vanishing amplitudes in the expansion of the state in stationary states. Realistically, we would have, if you take an ordinary pendulum like that and you give it a jog, the energy will be uncertain by zillions of values of h bar omega, and many of these coefficients will be non-vanishing. So more generally, we're going to have that psi is equal to, it will have many terms, and let's just write down a few of these terms. an minus 1 e to the minus I en minus 1 t on h bar plus an e to the I en, etc. So there will be many of these coefficients, but if we know pretty much what the energy of the oscillator is, right? We've lifted our bob up to 30 degrees or something and let it go. The energy is not completely undetermined, and what that means is that many of these will be non-zero, but they will all be clustered around some particular value of n. So that if you look at the value of one of these amplitudes, the modulus of it, as a function of n, you'll find that you'll get a pattern sort of like this somehow, right? There'll be an n at which the amplitudes peak, and there'll be small values here because we're pretty certain the energy isn't that small, and small values here because we're pretty certain the energy isn't that large. So that's the generic situation. And when we come and calculate the expectation value of x, what we now have is the same sort of thing as up there, but it's somewhat more complicated. We're going to have an an star a n minus 1, sort of the things that we had before, e to the I en minus 1 t on h bar times some matrix element n x n minus 1. And then we will have, actually I wanted to do this the other way around, didn't I? And then I need to put in a minus sign there. Right. Then I will have, the next one I will have, because nxn will vanish, the next one I will, by this symmetry property, I will have an plus 1 star an e to the minus I en minus en plus 1 t on h bar times n x n plus 1. And then I will have, not plus, it's not equals, but plus, a n plus 3 star a n, this will be the next term, e to the I, e n minus e n plus 3 t over h bar n x n plus 3 plus dot 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 dot, right? This is a specimen of a disgusting expression which would give us the expectation value of x. So this combination of terms we've already seen. This is nothing really new. The harmonic oscillator had just this kind of thing. In the case of a harmonic oscillator, this energy difference was exactly minus this energy difference, making this exponential and this exponential complex conjugates. They will not now be exactly, this will not be exactly this, because this is the difference between n and n minus 1, and this is the sort of one step in the ladder, and this is the size of the step one above it in the ladder, which will be slightly smaller.
Sorry, I think you have your browser text the wrong way around, didn't I?
Oh, thank you. Yeah, I have. That's right, because I changed my mind how I was going to do this, didn't I? Thank you very much. So this should be n plus 1, and that should be n, and this should be n plus 3. Okay. It's good to know that there's understanding in the room. So, so that's one thing that's going to happen, because this is a more realistic oscillator, is these frequencies will be changing. And this, crucially, this frequency here will be present, where it wasn't present in the harmonic oscillator case. In the harmonic oscillator case, this number here vanished. In principle, this would have been here, but this matrix element vanishes for the harmonic oscillator. But it's not generally going to vanish. It's going to stick around. Now, that has an important consequence, because this frequency, so En plus 3 minus En, is going to be on the order of 3 times En minus En minus 1. Right? Because it's the difference, it's 3 steps on the ladder, and that's only 1 step on the ladder. And if we think of the size of the steps in the ladder becoming small only gradually as we go up the ladder, which will be is a good picture to use, then this term is going to be essentially 3 times the frequency associated with the other 2, which we can regard as about the same. So when we assemble all this stuff, we're going to find that x, the expectation value of x, looks like some number times cos of En minus En plus 1. No, let's declare this to be 3 omega n, right? So we're defining omega n to be this quantity here. And we're going to find that we have a cos, some term like cos omega nt, and we're going to have some other term with some other coefficient times cos 3 omega nt. And we're going to have some other term with x5, some other coefficient times cos 5 omega nt. So that this number will depend on, will contain products of stuff like an plus 3 star and an plus 3, an plus 5 star, etc., right? And this will contain things like an plus 5. But we will have these other frequencies present, and this is what leads to, so this series implies periodic motion, but anharmonic motion. So in a musical instrument, the motion of the string in a piano or the vibrations in an organ tube or a flute tube or whatever has a well-defined frequency that sets its pitch, but the particular tone of the instrument is determined by the characteristic numbers of higher harmonics which are present, because it's an anharmonic oscillation typically. But there's more that we can do here, which is connecting to classical physics, which is to make the point that if we arrange this stuff, right, so this expectation value of x, we take out the leading term, we say that this is e to the minus I omega n t, and then we're going to have some sum. No, sorry, it's better than, it gets very complicated if you think about the expectation value of x. It's easier if we think about psi itself as a function of time. If we look at psi itself as a function of time, we can take an e to the minus I e n t on h bar out, and we can say that this is ... a n plus e to the I e n plus 1 t on h bar n plus 1 times a n, sorry, this needs to be let's need a minus sign there. I need a t on h bar there. So I've taken a common factor out. So this one doesn't have any exponential. This one should have its proper exponential minus the thing that I've taken out. The next one should have, and this should be an plus 1. This should be plus an plus 2 e to the minus I en plus 2 minus en t over h bar n plus 2. And so on and so forth. So to a lowest order approximation, these differences here are all multiples of a common frequency, and after a period, so when en t over h bar is equal to 2 pi, these things, n plus 1 minus en. After the time it takes for this to come around to 2 pi, this will have come around to 4 pi almost, and so on and so forth. And so the wave function will look, all this sum will be the same as it was at t equals 0, because all of these exponentials would have come around to 1 again. That's in the case that these things are all multiples of the same frequency. But as we've seen, they're not quite multiples of the same frequency. This is slightly smaller than twice this. And so in the time it takes for this one to come around to 2 pi, this one isn't quite round to 2 pi. and even more so further down the line, and therefore the wave function isn't quite back to where it was when at t equals 0. And as time goes on and we count more periods, so this becomes 2 pi n, these discrepancies become more and more and more important. And these terms down here, when this one has come round to 2n pi, this one will be significantly off 2n pi, and this one even more so. And that means that the wave function is not returning to its original value, and we're looking at motion which is not periodic. And whereas initially, because we'd released our particle from some particular point in the potential well, these wave functions all constructively interfered here at a particular value of x. After a certain number of basic periods, the interference, the constructive interference here and the destructive interference everywhere else will become less and less exact, and the distribution of our particle will become more and more vague until after a very long period, the phases of these will be essentially random and we'll have no knowledge of where it is. And this is precisely mirrored in classical physics. In classical physics, the small uncertainty in energy that was associated with having more than one AN in this series was associated with a small uncertainty in period. If the energy was very high, the period would be very long, and after a long time, the particle would have gone around and around a million times, and a million and a bit times, and here it would be. But if it was a slightly different, a slightly lower energy, it would have a slightly higher frequency, and it would have done a million and one oscillations, and it would be over here. So that you can see that this small uncertainty in energy is going to lead after a long time through the small uncertainty in period to a large uncertainty in phase and a total scrambling of our prediction of where it is. So again, quantum mechanics is returning in a rather complicated way and through quantum interference, a result that we're very familiar with if we think about the classical situation. It's time to stop.